Welcome. Hi, today I'm going to talk to you about probabilistic gradient boosting machines for large-scale probabilistic regression. My name is Olivier Sprangers, and I've done this work jointly with Sebastian Schelter and Maarten de Rijke, and we are part of the Universiteit van Amsterdam and the AI for Retail Lab in Amsterdam. So let me start by telling you what it is we are interested in. So we are interested in probabilistic regression. What does it mean? Suppose we have this time series, then we would like to know what is going to happen in this blue rectangle. We want to estimate that, we want to forecast that, and we want to do this probabilistically. And what does that mean? We want to have some notion of the uncertainty of that estimate. So we don't only want to provide a point estimate, so for example 200, but also plus or minus 10. And how are we going to do this? In this work, we're going to do this using gradient boosting machines, GBMs. So what are gradient boosting machines? Gradient boosting machines are just ensembles of weak learners. And we commonly use decision trees as base learners. And why did we actually choose these models? Well, one of the primary reasons is their superior performance on regression problems in forecasting competitions. And a recent example of that is the M5 forecasting competition. So a quick recap of decision trees and gradient boosting. So what does decision tree learning do? So in gradient boosting, we try to build multiple decision trees. So what you see here in the picture on the left is a tree where we split the data based on the feature age, and we split it according to the value of that feature, whether the value of that feature for that particular sample is less or higher than 15. And subsequently, we split data again, whether the feature for that sample has an attribute that reads yes for male or no for male. And by doing that, the sample indicated by our boy ends up at the bottom left. And this is called a leaf. It's assigned a weight, and the weight in this case is +2. After learning a single tree, we construct a second tree where we do the same thing. We again iteratively split the data based on features, and then we simply aggregate these predictions. So we have a prediction +2, and we have a prediction +0.9 for the boy, and the final prediction for the boy sample is then 2.9. So in gradient boosting, we iteratively build these trees, and each new tree is basically built to correct the errors of the previous tree, and our final prediction is just the sum of all the predictions of the trees. So if we look at probabilistic regression using GBMs, what do existing methods do? Well, if you see that existing methods for probabilistic regression, they typically require multiple models, or they are limited to small data sizes. So if we look at popular packages such as XGBoost or LightGBM, they commonly use quantile regression. But this requires creating separate models for each desired quantile. So in order then to get a full overview of the distribution, you need to train a lot of models. And this is computationally expensive. Then we have BART, which is a Bayesian model, but this is limited to small data sizes due to its computational intensity. And finally, we have NGBoost, which is a recent method that employs GBMs to predict parameters of a chosen fixed distribution. It employs multi-parameter boosting, so it actually optimizes multiple parameters, and it requires calculating a natural gradient to fit a desired distribution. It sacrifices a bit of point performance for probabilistic performance, and implementation is actually only limited to small data sizes. So the question that we asked ourselves is, can we actually generate high-quality probabilistic predictions with gradient boosting machines more efficiently? And what does this mean? So can we do this using only a single model? So drop this disadvantage of having to train several models. Can we do this with single parameter boosting, so not having to optimize multiple parameters? And can we do this with limited additional computation, so by not requiring extensive additional computation and or storage of a lot of parameters? And the answer is yes, and we will show this in the talk, and we introduce a method called Probabilistic Gradient Boosting Machines, or short PGPM. So what does PGPM do? So in short, in PGPM, we treat the tree leaf weights as a stochastic variable. So on the left, we have vanilla gradient boosting machines, GBM, and on the right, we have our method, PGPM. So in vanilla GBM, the leaf weight, so the prediction of an individual tree, recall the example of the boy I gave, is ultimately given by the sum of the gradients of the samples that land up in a leaf divided by the sum of the Hessians plus some regularization constant lambda. Now we can rewrite this equivalently as the sample mean of the gradient divided by the sample mean of the Hessian plus, again, some regularization constant. And I will show you why that comes in handy later. Now this is for vanilla gradient boosting machines. What we do in PGPM is we actually say this leaf weight is a stochastic variable that we are going to approximate. So we're going to say, listen, we have a mean, mu, and we have a variance, sigma, or sigma squared, I should say correctly. And we want to know the expectation of this random variable. So we have this random variable, the mean of the gradients that end up in a leaf, and the mean of the Hessians that end up in a leaf, and we can simply estimate the expectation of that ratio of random variables. And we can do that as follows. We show the formula for the mean and for the variance here, and we show the derivation in our paper, and it actually comes down to simply doing a Taylor expansion of the ratio of two random variables. So now we have obtained basically our leaf weight as a random variable. But now how can we obtain our final probabilistic prediction? We do that, so we generate predictions by sampling from a distribution which we parameterize using this learned mean and variance. So in vanilla gradient boosting machines, our estimate after k iterations for the sample I is given by our previous estimate minus the learning rate alpha times the leaf weight for the current tree. Now, in probabilistic gradient boosting machines, in our method, we do the same thing. However, our estimate is simply a sample drawn from a distribution parameterized using these mean and variance that I showed on the previous slides. And these means are simply the aggregates of all the means over all the trees. So for the mean mu, that's simply the mean mu of each previous tree minus a learning rate times the estimated mean of the tree that we just learned. That's what you see in the second equation of PGPM. And then in variance, the third equation of PGPM on the right, is similar. We simply aggregate all the variances that we learn in each tree to arrive at the variance of our learned variance after k iterations. One important thing to notice for the variance, we add a term on the bottom right that indicates the correlation existing between two trees, which can be seen by the term 2 alpha rho times the variance of the previous tree times the variance of the current tree. This is important because we need to assume some correlation existing between subsequent trees. So let's do a quick recap. So by doing this, by simply treating the leaf weights as a stochastic variable and using these update equations, we have achieved our research goal at the expense of minor issues. So we can generate probabilistic estimates using a learned mean and variance. That's great. There's limited additional computation required. We just need to store one additional parameter, but the amount of computation during learning is very limited compared to vanilla GBM. And it's just single parameter boosting. You can just use the normal root mean squared error loss function, but you just save all these empirical statistics. Disadvantages is that we are limited to distributions parameterized using a learned mean and variance. However, we do not observe significant limitations. We will show that shortly. And there are, of course, a vast choice of such distributions available. Think about normal, student t, etc. Finally, we keep decision points in the tree constant. However, we do this intentionally as it's computationally very expensive to recompute. And the final limitation is, as I just said, this correlation between subsequent trees. We treat that as a constant across samples and trees. And this is simply the simplest approximation that works well in practice. So onto experiments. So what we did, we evaluated our performance on both point and probabilistic performance on a set of 10 common UCI regression data sets of various sizes. So we performed the experiments for 20 folds, except for the large data set MSD, and we report a root mean squared error score relative to the PGPM median. So in every of these plots, you can see the median score of PGPM is 1, and the rest, the other scores, the blue, which is XGBoost, and the green, with slight GBM, is relative to PGPM. What we can see is that the point score of PGPM is better across all the data sets than XGBoost, and it's comparable to light GBM, which is great, because this already means that we are better able to do point performance. But of course, that's not what we're interested in. We were interested in probabilistic regression. So how does it compare against XGBoost on probabilistic regression? On probabilistic performance, we see that we exceed XGBoost by an average margin of 15%. So same experiment. Now we evaluate on CRPS, continuous ranked probability score, which is basically a continuous version of quantile score. And we see that across all the data sets, we perform a lot better. So this is great, right? So we have a fairly simple method that just uses standard empirical statistics. We add these statistics, and then we just draw from a normal distribution, and we're actually able to learn fairly good probabilistic estimates. So can we further analyze what happens? So yes, let us first start with the output distribution. One of the benefits of PGPM is that it allows to optimize the probabilistic forecast after training by choosing an appropriate distribution. So what do I mean by that? So recall that our final estimate is given by drawing from a distribution that we parameterize using a learned mean and variance. But we can arbitrarily choose this D after training. So we did that in our paper. So what does this mean? So for every data set, we simply chose all these distributions. So what you see in the table, normals, UC3, logistic, Laplace, etc. And then we evaluated the CRPS score. Then we said, okay, the distribution with the lowest CRPS score on the validation set, that's the one we're going to use on the test set. And then indeed, you see that you actually can get better test set scores too. So for example, for protein, we see the protein data set. You see that the negative binomial is the data set, is the distribution that achieves the lowest score. And then it achieves also a better score on the test set. This is great, right? So we don't need to make assumptions about the distributions before training. We can just do that afterwards. Secondly, are we now more efficiently? The answer is yes. So PGM trains orders of magnitude faster than XGBoost on larger datasets. So our implementation using PyTorch can use both GPU and CPU. And what you see in this table, as dataset size increases, and for example, if we take the largest dataset Higgs, we see that we are orders of magnitude faster than XGBoost. We are even faster with our own CPU implementation and XGBoost. And we're actually comparable to light GBM, which is great because we are actually providing a probabilistic forecast. Whereas light GBM, this is only for one model. Finally, I'd like to present you with a short case study. This is the case study of hierarchical time series. Now, what is difficult about hierarchical time series? The issue is that it's difficult to make consistent forecasts. So for example, suppose we want to make forecasts for products. So in this case, Old Amsterdam slices of cheese, Gouda slices of cheese, and for milk, we may have several milk products. One of the issues in retail is that we commonly make predictions at the product level, but then we also need to aggregate these predictions up towards a higher aggregation, for example, category, department, and total. But often these forecasts are then not consistent, in the sense that it's often better to create a separate forecast for the total level, because if you aggregate the lowest level forecast, it's just, doesn't make sense. So how can we address that with PGPM? You can address that because our implementation allows much more complex loss functions, because we are able to use automatic differentiation. So recall the standard mean squared error loss function used in most forecasting applications. We just take the squared loss, so the square difference between our prediction of a sample I, and we take the mean of all these errors. Whereas in hierarchical time series, we do something similar. However, I'll show you an example for two products. We might have a loss for the first product, which is L1. We might have a loss for the second product, L2. And we also consider a third loss, which is basically the sum of the estimates and the actuals for these two products. This allows us to simultaneously not only optimize for the item level forecast, but also for the aggregations. However, if you were to derive a gradient and Hessian for this loss function, it becomes very difficult very quickly. And I've done it for this simple example, and you already see it becomes quite involved. So the more examples you have, the more levels you have, it becomes super difficult. This is where auto differentiation shines. And this is what we did on a sample data set of the M5 forecasting competition. It's a data set that consists of 3,000 products, 7 categories, 3 departments, and 4 levels. So for each forecast day, we are forecasting individual products, we are forecasting category, we are forecasting department, and we are forecasting the total level. So what do the results look like? So first, if we look at point performance, we compare PGPM against NGBoost and LightGBM, and we compare for the standard MSE and our weighted MSE function, which can now be optimized because our implementation allows automatic differentiation. And we see that our individual performance actually improves for the higher aggregation levels, which is what we expected, right? Even more interesting is that if we look at our probabilistic performance, the difference becomes even greater. So we're actually able to learn a lot better probabilistic estimates for these higher level aggregations, simply because we can allow far more complex loss functions. And this is good because now we are able to generate item level forecasts. We are able to generate item level probabilistic predictions, but all these item level probabilistic predictions are also already better calibrated with their higher level aggregates. And this is a big benefit in hierarchical time series forecasting. So to conclude, first, we've shown that PGPM beats the baseline on both point and probabilistic performance. It is an order of magnitude faster than the baseline on larger data sets, so it's really suitable for these larger scale regression settings. And our implementation allows a wider set of problems to be effectively addressed, because we don't need to calculate an analytical gradient and Hessian, and as is necessary in existing gradient boosting packages, we can use much more complex loss functions, opening up a wider set of problems. In future work, we would like to further generalize PGPM and work on the theoretical rigor over method. As I said, one of the limitations is that we make a few simplifications, such as keeping several things constant during learning. This is something we would like to address in future work. So finally, I'd like to conclude with an advice. Try it out for yourself. It is available as a pip installable Python package. So pip install PGPM, and the repository link is shown here. You want to reproduce the results of our paper, of course, also included in our GitHub repository. And finally, examples. We provide a lot of examples in the GitHub repository, including training PGPM on CPU, on GPU, on multi-GPU, on multi-CPU, and also on multi-node multi-CPU and GPU, which means you can scale your problem to infinitely large dataset sizes, where we see near linear scaling of performance. And again, we refer to the GitHub repository of examples thereof. Thank you for listening. I appreciate you taking time to listen to this call. Please reach out if you have any comments or would like to know more. Thank you very much. Bye-bye.